Andrew Dunbar, a brief about Andrew. Andrew is a senior structural engineer at Structex, based predominantly in Christchurch. Andrew originally joined Structex as a graduate engineer following the completion of his master's degree at the University of Canterbury, with the focus on multi-story timber structures. Andrew is particularly passionate about timber structures, and in 2019 returned back to Structex after a 2-year sabbatical in Vancouver in Canada, working there at Fast Epp, renowned for pushing the boundaries of mass timber. In Vancouver, he furthered his expertise in mass timber structures and was involved in several large projects, and has returned to New Zealand to continue the push towards mass timber in the New Zealand context. Once the presentation is finished, we will have questions and answers session. You may like the published questions to determine which goes first in the queue. Thank you very much once again, and please allow me to welcome Andrew Dunbar. Andrew.
Cool. Thanks, Namir. And hopefully this works. Next slide. And thanks everyone that's tuned in. So my presentation today is effectively a bit of a story about my OE, so thank you for tuning into that. Hopefully is a bit more on a professional context. So the outline today, I've tried through the presentation to have almost no words, so this is my picturama version of that. So I'll talk a bit about some of my background in timber, which has been partially introduced. Some of my observations from my time working in Canada and in the kind of timber industry in general, and then go through a couple of case studies. The first one is the Fast Epp new home office building in Vancouver, and the second one is the Keith Drive office building in Vancouver as well. So some background. For me, I did a master's out of Canterbury University at the end of the STIC program. So looking at post-tensioned Clt shear walls that run out of LVL at that stage, and Clt was coming out of Nelson, so we managed to get our hands on some. In this case, looking at stair wells and lift cores and pushing those around. Then I worked for Structex after leaving uni for a couple of years, working on a variety of timber, concrete, steel buildings, but some timber, including the Christchurch Adventure Park buildings that some of you may be familiar with. So I kind of took some general learnings from all that and my masters. One thing which I've found, some people say that timber isn't that recyclable. I've found plenty of opportunities, especially for the post-tension Clt walls, make great tables, kind of even with voids for post-tensioning strands. But anyway, so I thought I wanted to pursue kind of broaden my horizons in timber a bit. So then I thought, what has lots of trees, what's still in a seismic region, where do they predominantly speak English, and where can I convince my wife to go? And that was Canada, and a company called Fast Epp, which was put onto me. So Fast Epp, is a slide from one of their buildings, which I'll talk about a bit in a minute. They're a company kind of started out of Vancouver, have other offices in Edmonton in Canada, along with New York and Seattle in the States, and in Germany as well. And they have been known over the years for pushing the boundaries in timber. And the building you see here, we'll just run through a couple of quick case studies from kind of their back catalogue, which were done before I was there, but this building was completed just before I was there, so we're getting quite a bit of press about it. It's the Brock Commons building, or Tallwood House in Vancouver. It was a student accommodation block. It was 18 stories tall, and it was built maybe 2017 or something like that. So at the time, it was the world's tallest building, timber building, which was a great feat. I guess I would say it did have a concrete core though, or 2 concrete cores for the lateral system, but certainly the gravity structure was full timber for those 18 stories. This one was quite an interesting one, where they managed to get rid of all the beams. So it was just using internal columns and point supported CLT, which certainly has its own challenges and requires quite a lot of columns. But being a student accommodation, that was easily accommodated within the room layouts. From a constructability perspective, the building went up really quickly, kind of at least a floor a week, I think is how they were moving, with only 3 or 4 guys on site. The crane would drop in a whole bunch of panels, lay those, then drop on a pack of columns, and the guys would stand them up, and then the crane would go away and be lifting in the facade panels on a couple of levels below, and it ticked along nicely like that. So there's plenty, if you want to look at this a bit more, there's been quite a few webinars and that sort of thing, probably through the Woodworks Canada organisation that you'd be able to take a look at, but certainly worth some investigation. Another favourite of mine from Fast Epp's history is this building, which is an aquatic centre in the wider Vancouver area. Probably the main feature of this, which I think is quite fascinating from a timber engineering perspective, is the use of timber beams and a catenary action, so spanning 55 metres with only 250 deep glue lambs, which is pretty unreal, I think. So it's just a couple of pairs of glue lambs running across, and a bit of plywood on top, and to achieve those spans is quite amazing, I think. And it also looks great from the underside, and I don't even mind the concrete even. So yeah, a couple of quick examples of Fast Epp's kind of some of the things I've done. It's only a small snapshot, but gives a little bit of a context of the sort of things that they get into. So next is a few observations from my time there, as a kind of in a general sense or at a high level. Firstly, which I think probably most people are aware of, is the natural resource that Canada has with their trees. So there's a couple of images here on the left, just some sort of map off Google showing the extent of the forests that they've got available, which is absolutely vast. When you think about a 1 million, 2 million people live in a tiny dot in the bottom left of the page, and then compared to the New Zealand size of New Zealand on the right, the country's just huge, and they've got a really old lumber industry. So it's well advanced, and they benefit as well from the native trees being the stuff that makes really good structural timber. So flowing through from that, the supply chain then is quite well established. This is just a little shot of more the mass timber suppliers. There'll be tons of other timber mills and smaller timber suppliers, but these are the main kind of mass timber people in the game. Typically centered around each coast, so the west coast and the east coast, and which does influence the type of material that they get. So often Douglas fir on the west coast, which is a bit stronger and stiffer, and then spruce on the east coast. But it is possible to get either on both coasts, but that's kind of where they grow. Then the sort of products that you can get is the obvious kind of CLT and glulam, those two on the bottom left there. As well, they do a little bit of LVL and parallel strand lumber, that sort of thing, but it's not widely adopted. Mainly the glulam would be used for beams and columns. Yeah, a lot less of the LVL than what we see here. Other products which have been used for a long time and are still used as products like nail laminated timber, or NLT, which is a shot of this, the kind of middle image there, which is just a whole bunch of boards laying up beside each other and nailed in. So that was often used in old warehouses from 100 years ago that are still standing today, and it looks really great from my perspective, but that's still an option over there. And then a relatively newish product on the market, which I'm saying relatively new, it's probably 5 years or so been up and running, but is Dow Laminated Timber, which is on the right there. So it's a whole bunch of boards, again, running the same direction, and with some hardwood pins that are fired between them to hold them together. So there's no glue, no nails, so it's an all timber solution, which is quite cool. So yeah, they really benefit from kind of a wide range of suppliers and a wide range of potential options that are available locally. Another key point from working over there is, I guess, earthquakes. So on the west coast of Canada and the west coast of the US is kind of a similar seismicity to New Zealand in a lot of parts, on the other side of the Ring of Fire. From a design perspective, they certainly design for earthquakes. It's all through the codes, and people do it. But what I found was, in a general sense, that sometimes they allow for earthquakes in the design at the time, but they're not always thinking about what would happen after the earthquakes. So there's still a bit of kind of ductile concrete shear walls and that sort of thing going on. So probably what I always thought was what happens here in an earthquake. This is downtown Vancouver, whole bunch of large buildings. A lot of them would be ductile concrete shear walls or frames. So there's kind of on the right hand side is the office towers, and then the left side is all apartments. So it always kind of grabbed me thinking about back to Christchurch, of how many open or demolished buildings we had, and then what would happen in Vancouver here if that happened as well, and where do people go, is my big question. So that kind of is my high level take on a couple of aspects of Canada, so in the supply. So that frames in hopefully to a couple of some discussions on these case study buildings. So the first one I'll talk about is the new Fast Epp office building in Vancouver, which is I think finished now, and they're in it, which is cool. So my involvement on this one was through the design up until the construction phase, and then I think they were starting in the basement construction when I had to leave to come home, but it's all done and dusted now. So a bit of an overview. It's 4 stories over a 1-story basement, and it's on a really long, skinny site. So I think it's only about 12 meters from front to back, but something like 40 meters in the long direction, and a kind of a little bit of a slope down from the right-hand side to the left-hand side. So the building use is predominantly office with open spans from one side to the other, and a bit of a mix of materials from concrete, steel, and timber. Trying to use them predominantly where they make sense. And another big part of the kind of design mantra of the building was it was in some ways a little bit of a test case. So they're happy for it to be a bit somewhat experimental and pushing the boundaries, kind of reflecting a little bit what Fast Epp have done in the past. So I'll talk about the different aspects of the structure in a minute, but one aspect of the kind of architecture employing that was the use of some dynamic glazing, which is kind of on show in the shot here, with where they can turn on and off the shading of the windows depending on the sunshine to control the heat. So in terms of the gravity system of the building, highlighted here are the Clt shear walls, or just Clt walls through the building. We have some stair and lift cores on the left here, and on the right hand end, a couple of feature panel walls in the front, and a boundary wall along the back, which is also formed with Clt. So that wall is a boundary wall and a property wall. So it has a 120-minute fire rating, which typically in New Zealand we wouldn't do that in Clt. We would probably, the default would be to have precast concrete panels there. But the feel from the Canadian industry and people higher up above me and from the owner's perspective, that was precast concrete was relatively expensive. So this was seen as the cheaper option. And obviously precast, if those are precast panels, that significantly alters the weight as well. So it would have large impacts, I think, through the rest of the structure if that was concrete. So those walls were at the back there, typically 145 thick. They were kind of pushed down to the limit as much as possible. And then there were some other walls which were a bit thicker, more like 245, 7 plies or 9 plies in the main lateral system walls, which I'll talk about in a minute. And yeah, so that was the main walls. Into the floors, we had 3 suspended floors and a roof, all from Clt 3-ply, about 105 mils thick, spanning about 3 meters between primary beams, which is a really efficient span for that material thickness. On top of those, we had an acoustic mat, and then 50 mils of concrete topping. So that seemed to be how they would deal with acoustics in the majority of cases, and in a lot of these buildings was that sort of system. I don't think it's perfect, I'm sure, and I don't know what the STC and ICC ratings are for them, but it seems to work quite well. And again, they're happy for a bit of an experimental approach that would be able to do something about it if need be. So that's typically the Clt spanning 3 to 4 meters is probably upper range of a 3-ply Ideally, you keep it to 3-ply if you can. And then the acoustic mat and a concrete topping were how the acoustics were dealt with in this case. So the primary beams, all glulam spanning from one side of the building to the other, so up to kind of 11.5 meters in most cases. Designed for fire, so I think 30-minute ratings for the upper ones and maybe 60 minutes for the lower beams. So we utilised the char of the timber to provide the protection here, to keep all the beams and the floors exposed. And obviously the CLT also has to provide that char rating. So in some cases you don't get left with that much wood in the CLT floor, but still works. Into the columns supporting those glulam beams along the front was steel circular sections, which were kind of a bit skinnier behind the glazing and helped support that as well. So it was really kind of the right material. A glulam column in there would have worked as well, but would be significantly chunkier. So there were glulam columns on the back to help support the beams, and they were kind of a semi-composite with the back wall, which were helping in the fire case as well. So looking through a cross section of the building here at the beam kind of column elevations, we've got our glulam spanning right across, relatively chunky members to control kind of deflections, probably is the main one. And connections at each end were done with a group of bolts, which were set down in the section to reduce the need for, or not have to have any other screw reinforcing and control splitting. So we could have set them a bit higher, but we probably would have had to use some screw reinforcing, like I think some of our presentations earlier in the webinar series. And these bolts as well were required to be fire rated, so we had to set them in a certain distance to allow for the char of the timber around it, and then they would be plugged with timber plugs. And the steel was intermittent painted and painted around as much as possible, the interaction with the glulam. On the back of the building side, there was a little bracket with a similar connection into the beam that hung off the timber column, which then had another timber column stacked on top of it. So relatively simple to erect. We did look at tight fit pins here, but they're a bit harder to install, and it usually takes a bit more craneage time. So we went with bolts in this case, but effectively the design is fairly similar for that. Now, so looking at a construction shot of that installed, you can see the glulam beams across, a whole bunch of holes for the bolts, which are yet to be plugged, our steel columns, and the exposed CLTs. So I think apart from the floor, the top of the floor down the bottom there, it's pretty much the finished product. Obviously a few lights and stuff hanging down, but it's really the structure on show in this case. So another part of, which I'm sure everyone will be aware of for these long span and relatively lightweight floors, is vibration is quite an issue, or can be quite an issue. So the beams were designed for strength, obviously, and for the nominal deflection guidelines, but from some analysis, there would be certain frequencies where the floor would behave relatively lively. So some vibration testing was done. There was some prototypes that were done in a yard offsite with just the investigating the effects of having the beam and the CLT on top of it, and then what the effects of screwing in and kind of how much composite action you get, which it doesn't take, and from a vibration perspective, it doesn't take that much to get composite action because the loading is so small of a person that a screw into the top or a few screws into the top can often provide a composite action between the CLT and the beam that we wouldn't account for from a structural design perspective. And then they took that initial testing and also did some testing in situ on site and measured the effect and the influence of adding the concrete topping as well. And then I think the intention is that they do it with the fit out in place as well and see what frequencies they get out of that. I don't have results of the vibration analysis, but we can probably put you in touch with someone that does, and I'm sure there'll be a paper or a presentation coming out on that out of Canada at some point. So now into the lateral system, which is largely done by Clt Shear Walls. So we've still got our boundary wall along the back, which is a whole series of walls, and then we have a series of these red walls, which are marked on here, which are perpendicular to that for the other direction. And of note here is that the two big walls out the front, which you would think look like shear walls, are just gravity walls, and we didn't use them in this case, which took me a little bit to get my head around. I didn't really like the eccentricity of the system. And thinking back to some of the lessons from Christchurch, it's certainly to try and avoid that where possible. However, in this case, part of the limitations on the lateral system were that along the boundary to the top of the page here, we could only deflect about 100 to 150 mils at the top, which is only less than 1%. So in the end, I came around to a long, big, skinny wall with a whole bunch of other walls helping resist the twist. So the system start if we ignore the big dissipator in the center of the page there for now. The original system didn't necessarily start out or target to be a low damage system. In the Canadian code, you're allowed to, for shear walls like this, you can have a ductility of around 2, and then they have an overstrength factor as well, which gets applied to that of about 1.5. So it's kind of the equivalent of our SB factor. So it'd be like reducing your lateral load by a ductility of 2 and an SB of maybe 0.6 if it was a direct comparison. But it doesn't really give you, it allows you to do that ductility, but doesn't give you a whole bunch of commentary on how to achieve it. So the options are some sort of screws into steel plates potentially that will yield, but get pretty sloppy as they yield, and after an earthquake there's not really much stiffness left. Or there's dowel pins, which you could do in internal knife plates, which would yield dowels, but then after an earthquake, kind of how do you do that? Didn't really want to have to replace or tear these walls down after an earthquake from an engineering company. It's not necessarily a great look. So we kind of came, and it was good timing, we came to Tectonus, who were in which I was aware of from New Zealand, but not many people knew about it in Canada. So it was good timing really that we were able to integrate this within the system to give some resilience to the lateral system, and it helped me feel a bit better about the twist, that we had a reliable, resilient system that wasn't going to let go after a few cycles. and then the wall at the back was effectively designed elastically with splice panels kind of connecting one to the other, which I'll talk about in a minute. So a bit of a zoom in on the bottom of these, the shear walls. So we had our Tectonus devices. I think these are, from memory, were about 700 kilonewtons each worth, which were connected to knife plates up into the CLT with a whole bunch of tight fit pins designed to the overstrength of the Tectonus device. So from what I hear, I think the installation of the devices and the connection between the plates is relatively easy, but they did find it a bit difficult on site / in the shop to install all these pins, because there can be if there's a bit of variation between the CLT where the holes have been drilled by a CNC machine and the tolerances of the steel plate, which may not be as tight. There can be some persuasion that needs to happen to get some of those pins in. In terms of a shear key, you might see there's a little concrete plug in the middle. So we used that as our shear key. We just left some bars sticking out of the foundation, and then they came back and filled in that hole. So you'd see as well, probably from this detail, it's not necessarily a pure rocking system, that there will be a bit of, maybe it'll bind up a little bit on that shear key, but with the deflections, kind of trying to keep them to a really tight limit. We weren't too worried about that. There's a couple of shots of the walls going in place, which I think went pretty quickly. They came pre-installed with the knife plates, and they just bolt them together to the Tectonus, a little bit of tolerance in the bottom, and yeah, put them on the crane and a couple of guys pushing them around. It went quite well. The back wall here, again, a series of panels beside each other. The connection between each one was typically a plywood spline join with just nails and screws holding them together. And then typically you can see here there's a few columns which are usually lined up over the top of the joins. So in an earthquake, we're expecting these to be largely elastic. If there ever was to be a really large event and you needed to try and strengthen these, we would expect that you would just put some brackets in on each side, or just re-nail the existing or re-screw the existing joints. And that's kind of the extent that we would expect to see. So we found this along direction isn't necessarily low damage, but one of the main modes for the along direction is a twist, which is then countered by the Tectonus and rocking walls. So we felt quite comfortable around how the system would perform, albeit not a traditional or a full kind of complete no damage design, but certainly a increased resilient design. Through construction, shots here, I think some of the original goals were to try and have the superstructure go up in about a week. I think it was a little bit slower than that, but partially affected by kind of COVID requirements, I think. But it was still very fast in a matter of, I think, less than probably in the kind of 3 weeks type range to get from the basement slab or the ground floor slab to panels on the roof. Was very fast. And then the kind of final pre-construction shot, again, pretty much as all the beams, columns, and the floors all exposed in the final case. And then looking at the completed building, pretty much as it is now, I think. Yeah, so that's the general gist of the Fast Epp building. Relatively quick overview, but I'm sure there'll be some questions about it. But yeah, probably in summary was main drivers were speed of construction, utilizing materials in the appropriate manner where it makes sense, and looking at some increased resiliency in the seismic design and being a little bit experimental and pushing the boundaries. So the next case study, which I was involved in, was this building for Keith Drive in Vancouver. So I was involved through the design of this until about the kind of consenting type stage. And then I was on a flight back to New Zealand. So since then, it has progressed a bit with some component testing, further analysis, and through the consenting or building permit phase. And I think it's in the ground now, getting started. So in terms of the building overview, it's a 10-story structure over 4 stories of basement parkade, situated on a sloping site, which is about it's relatively significant, over about a story or 3 or 4 meters from the back to the front. The template is pretty much an office layout, so targeting large open spaces, not too many impedances through the layout, and then a key driver was the kind of expression of the structure into the architecture. So the general structural system is looking at a kind of traditional post and beam for the gravity structure, then mixing in some lateral bracing around the perimeter, which was expressed and made part of the skin from an architectural perspective, and was really probably from quite an early stage. This sort of imagery hasn't really changed. So in terms of the gravity system, we had glulam beams supported on glulam columns kind of around the perimeter, steel flush beams through the middle so that didn't poke down beneath the floor, and then CLT floors spanning directly from one side of the other. So this one's a bit different than the other Fast Epp building, where we're doing 8 meters directly in a CLT panel, which is not necessarily the most materially efficient, but does allow a really clean ceiling from the other side, and potentially does save some height of the building, that if we had to have beams spanning across, secondary beams spanning across, and then CLT on the top, you might lose 300 or 400 mils each level. Times 10 stories is another floor. So there can be efficiencies in using this, as well as we needed 2-hour fire rating, so the thickness of the panels helped there. So looking at the panels a bit closer, we did use a bit of trickery to try and reduce the volume of timber or of CLT spanning across here. So in a lot of the Canadian suppliers, they tend to make their CLT panels in kind of billets, so they'll be could be 3 meters wide and 2.4 meters wide would be typical panels. So sometimes if you had a 2.8 meter panel, they would make a 3 meter one and cut it down, so you get a bit of wastage. So what we tried to do here is took kind of a hit and miss approach of a 300 thick CLT that was 2.4 wide, some little notches in the top, and then a 800 mil section of 3-ply CLT, which would basically span between the two, which would then which was also divisible by 2.4, so they could cut it out of a 2.4 panel, and then that allowed some room for a service chase that can go across the building through that space, and also breaks up the ceiling a little bit from the underside. In terms of the beam column connections, from column to column, we used a steel SHS that kind of joins one to the other. So that was something that came out of the Brock Commons building that worked quite well on there, where you have pretty much 1-story columns that you can stack up and handle easily, and allows people to do it on site while the crane's doing other things. Then we had our beams coming in to the column using a pre-engineered off-the-shelf product, which in this case was a Megant, which originally out of Germany. So the column would come with one side all screwed into it, and the beam would come with the other side, and then on site you click it together and run the bolt through it, and you end up with a fully concealed connection, which is then also fire rated by the timber wrapping around it. So that worked well through the building, and certainly helps through the design side. And then CLT sitting on top of that with a bit of concrete topping and an acoustic mat, similar to the Fast Epp building on top of that. Through the central beams, we had these steel flush beams, which was an SHS section with a big fat bottom plate on it for the CLT to sit on, and then that connected across and sat on the timber columns, little bolt through. So yeah, key drive was to try and get a clean surface through the bottom to run the surfaces. So if I come to the next slide, this is kind of an image, a render of what the intention was for it to look like. So we can see the surfaces chases through there, and a bit of a bulkhead to hide some surfaces which would be shot out from that zone. And then another nice render of what the intended product is supposed to look like, with nice people and furniture in there. So the lateral system involved, well, one of the key drivers from the project was to make a all timber lateral system, which is kind of pushing the boundaries for what has been done in seismic regions from around the world, being 10 stories. So we have quite a regular perimeter brace frames, and then a series of internal Clt shear walls. So for the brace frames, again, I think this was well outside kind of code allowances, but there was another avenue to do it. But the recommended ductilities was 2 with a 1.5 over strength, similar to the previous building. So the original strategy was to use a yielding steel mechanism with some perforated plates that would yield through the movement. However, through some physical testing, that kind of didn't provide the level of robustness that was needed here, and again would require some significant work to replace it after an earthquake. So the decision was made to go to a Tectonus system on the back of the previous building's successes. So in the brace frame, this is kind of the typical detail. So for the brace, we had a double Tectonus unit with a telescoping kind of SHS tube here to allow the movement in and out, but provide some stability to that brace. That was connected in through a large knife plate which traces through the column, and a whole bunch of tight fit pins that are hammered in there, and some bolts. So quite an involved connection, but some quite large forces going through it. And I think it would be interesting to see how this comes together on site. I think the intention would be that the knife plate comes all nicely done with the column, and then you bring your beam in and can bolt that on. Bring the beam in from the right hand side and connect up the nice easy magant, and then go from there. We don't have heaps of time left, so we'll push on into the Clt shear walls, which are obviously relatively large here. So they're made up of, you can see kind of the alternating colors there, which are denoting different Clt panels. So pretty much 3 panels wide. I think in total was maybe 7 meters wide, something like that. And then a few stacks of panels. So up the height there was connections, tension connections at different levels, and shear connections between panels, pretty much up and down the whole walls, with a big base connection at the bottom, which is this one here, using Tectonus as well. So this connection changed a bit since I left, but I think the principles are fairly similar. So we've got a big concrete wall from the basement below, and we have some Tectonus devices at each end, which are then connected into a steel column. So that connection is relatively easy, steel to steel. And I think the hold downs we needed here were in the order of something like 2,000 kilonewtons. It may have been more in the final design. So we've got that huge load getting transferred into the steel kind of boundary column element, which then has to be connected into the Clt panels. So this is a hold down basically going over 1.5 stories. It kind of gives you a bit of a picture for what the load is that needs to be transferred, and kind of some of the difficulties sometimes in getting large loads into timber. Through the middle here we have the kind of little spine plates which are screwed on the front or bolted on the front, and down the bottom we have this nice idealized pin which is anchored into the bottom of the Clt panels with a series of little kind of gussets that are grabbing the Clt and using the bearing. So in this case, this is a lot more of a nicer seismic system, I think, than the previous building. But this one has a lot more riding on these connections, and really needs to perform well. So I think a lot's gone into this, including physical testing, ruling out other options, and I think it was found that Tectonus, or in this case, kind of gave them what they needed. I'm sure there are other ways, but this seemed like a good product at the time. So that's kind of the main bits from that building, which was a relatively fast flick through it. I'm sure there'll be some questions on that, which we can cover off. But I wanted to say a little bit of a spiel here for both of these buildings, the support that they got. So they both benefited from some funding supplied by Natural Resources Canada, or NRCan, which went towards kind of progressing these mass timber buildings. So you could get funding for things like extra design that would be required for timber that you wouldn't have to do for steel or concrete, or extra things that you might have to do on site, like some weatherproofing and stuff that you wouldn't have to do for steel or concrete. But it didn't go specifically towards the actual construction cost or material cost. But we found it really allows these buildings to kind of go ahead well, and provides kind of a lighthouse for other buildings or other people thinking about similar things, and had influences on code changes and that sort of thing. So in New Zealand here, I think we have the kind of MPI initiative with some funding available. So the first part of that is the Clearwater building out in Christchurch that Red Stag and others are doing and have been showing off a bit lately. And then I think the second parts of that part of funding is some further buildings. So my hope with those is that it acts in a similar way, that shows off the use of timber and allows for kind of some pathways and some guidance for others looking to use mass timber in the New Zealand context. So to summarise, my thoughts are in the mass timber realm, we would be trailing Canada for now. They've certainly got the advantage of the kind of hundreds of year old industry and the amount of natural resource that they have available, and also the quality of that resource, which is quite superior to the radiata pine that we have here. And the adoption of mass timber is relatively widely accepted, and it's not an out there thing to do for a number of building types. Second part is, I think from New Zealand, we've got a good head start on the seismic innovation that comes with designing multi-story buildings. And I think certainly it's showing that even in Canada, for the couple of these buildings, that we have New Zealand technology going into those. Third point is Canada certainly benefits from the reliable material supply. And I think in New Zealand in the past couple of years, we have probably suffered a little bit from that. But now with Red Stag kicking off and XLAM supplying in here, and a number of other suppliers coming up online, I think that I hope those problems are kind of getting behind us, and we can really rely on that supply coming through. And the last point is feels like we're getting close to some widespread adoption in New Zealand. People are certainly thinking a lot more about the carbon footprint of buildings and of everything in general, and part of that is the embodied carbon of the building itself. Operational carbon can obviously, in New Zealand as well, with a lot of renewable, is still an issue, but I think attention is getting turned towards the embodied carbon, and things like the Naylor Love calculator are helping, and there's a lot of conversations through architects and owners and the public about this. So we just have to be ready and have some good knowledge about designing in timber to help support that. So that's pretty much my presentation. So some acknowledgements. A big thanks from me to Fast Epp for firstly the opportunity to work for them overseas for a couple of years, and then supporting with a whole bunch of photos and slides to help with this presentation. And then thanks to these other project partners that were involved in the Fast Epp office building, And then for the Keith Drive building, the key project players and that. So that concludes my my presentation. So I think we can now is time for questions. I assume so. Thank you.
Thank you very much, Andrew. That was really very impressive. Your two projects greatly presented, and thank you very much for your hard work in Vancouver. That's really like good engineering practice there, and coming back to New Zealand to benefit from your expertise and services. We have 24 questions. Now it's 1 o'clock.
Cool.
And we have few left, but we will carry on until we finish all questions, hopefully. I do have a couple of questions which I hope you can answer at the very end. One is about, because I cannot like write questions, one about time frame for constructability of this type of projects, and the other one is the cost effectiveness compared to concrete or steel. So just leave it to the end. If there is no time, that's fine. Now,
Okay.
coming into questions, sorted from the most liked to the less liked. Number one, what's the diaphragm design process? And what rigidity is assumed from the diaphragm, and how the continuity of the diaphragm load path is ensured?
Yeah, so for the design of the diaphragm itself, or for each building, utilize the CLT as the diaphragms. So some of these cases, some people will use the concrete topping and put reinforcing in it to provide that diaphragm force. But in these ones, we use the CLT, and it was a fairly typical, I guess, the normal design process, kind of a strut and tie type thing that you would use to design any diaphragm. In terms of rigidity, we did kind of a boundary analysis of assuming fully rigid versus semi-rigid. It's probably, what we found is it's mostly towards the rigid side, but there is some flexibility in the connections, obviously, which brings it back a bit. So we kind of covered our bases with a bit of a boundary, upper and lower boundary approach to those. And in terms of the continuity of the diaphragm, we between panels, it would be like a plywood splice to take the shear, and then around the perimeters, we used a kind of continuous steel angle or steel member to maintain those chord forces across panel joints, which you could use the CLT for that, but you end up putting a whole bunch of fixings in one side of the panel, a whole bunch of fixings in the next, and a little strap, and then you pretty much join it up to the next strap as you hit the next edge of the panel. So we found it was most cost effective to use like a steel angle or something along the edges, which can also form part of the formwork to support the concrete topping.
Okay, next question. How did they clad the CLT in the boundary situation?
Yeah, so that in the Fast Epp building, that that had a prefabricated cladding system onto the boundary, onto the outside face. So they had the CLT came with insulation, some battens, and then a cladding system. My recollection is it was some form of kind of metal corrugated system, but I'm 100% on that. But it was a lightweight system, and then they patched up the spine joins. So there's, yeah, it came as a system allowing, assuming that we wouldn't have much access to that other side. There should be still access through the most part of the building's life, with the neighbouring building being residential, and it wasn't allowed to be commercial. So there should always be a clear way to see the back at least, but there has been some design in there from an architectural perspective to try and help mitigate any durability issues from that cladding.
Okay, next, for mass timber construction, is there additional durability issues other than moisture need to be considered? For example, insect protection, etc. Have we observed any detection, deterioration in mass timber as a structural material in a time frame, or maybe timber frame of e.g. 100+ years? Is there any documentation that we would refer to consider the deterioration in the long term? A little bit like not very clear.
Yes, so for from my perspective, I think the main issue is the moisture, and trying to limit it during construction, and certainly keeping it out through the building's life. In terms of other durability issues, insect protection in Canada is an issue given the climate, and I don't think it's as much of an issue in New Zealand either, although we do have borers still. But certainly for more tropical locations, we did at one point when I was there, we worked on a project in Mexico, and there was certainly concerns there about termites and how you can protect from that. So there are some surface coatings you can use, and you can also try and create a barrier for them to so they can't climb up effectively into that structure. In terms of structural material over time, I think the key thing here is to stop the water getting into any timber. And then if you do that, there's plenty of buildings around. I know through Vancouver, all the old warehouse buildings that used to be for train yards and stuff, which are now offices and fancy apartments and restaurants that have 100+, 150-year-old timber frames with brick cladding around the outside, and they've stood up well, benefited by I think protection from the weather. So there's certainly examples in New Zealand, I think, of 100-year-old buildings that are mainly light timber frame probably. And there are examples, I think, as well, where timber hasn't done that well, but it would probably be expected for that to happen where it was exposed to the weather.
Okay, another question: how is the 120-minute fire resistant rating boundary wall supported when floors have only a 60-minute fire resistant rating?
So I'm not. I think they utilised we had a series along the edge of that wall where the panels were also. There was a ceiling underneath, which provided some additional fire protection. They have slightly different rules here for the out-of-plane support of those walls. But my recollection is we used a part of the floor to provide a diaphragm to drag it over, but not utilising the whole diaphragm. Yeah, so certainly an issue. I think if we only had a 30-minute floor supporting the wall for outer plane for 120 minutes.
Yeah, a question saying, can you talk through the design basis of the floor diaphragm?
I think was that already covered, or I guess the design basis of the floor diaphragm again was utilizing the CLT to provide that diaphragm. And I think there's some guidance that has come out. I know Daniel Morota's written some papers on it recently about how you design diaphragms in timber. So I was kind of applying you can almost think of it as light timber frame, but then with big shear elements through the middle.
Another question saying, I see the short direction lateral resisting wall located in the stair void. Any specific detail to consider the dragging force for the connection at these locations?
So I think what we're asking there is if what the drag tie for and what the connection is from the floor diaphragm into the walls. So in that case, we used a steel angle that was fixed into the floor and dragged out turned into a flat plate that dragged out into the floor diaphragm, and then was fixed into the wall. Trying to concentrate the screws in roughly the center of the wall. So it's not we didn't aim necessarily for a perfect pin connection in the Fast Epp building. I know in the Keith Drive building, they went for a more idealized pin in that case, but I didn't have a proper detail of that.
Another question saying, was the low stiffness of the doubled plates for the tectonus connection an issue during design stage?
So I think what is being asked here is that at the bottom of where the tectonus connects into the steel plate, which has a knife into some timber, that there is before the tectonus engage, there would be a bit of movement in the steel connection at the top. So we did account for a bit of softening in the spring at the bottom in the analysis to try and account for that, but haven't done physical testing on that to know exactly the extent of what that would be, but we have tried to account for it in the analysis. But yes, it certainly happens where you have to be wary of the connection into the timber is also going to lose you some stiffness.
Yeah. Another question for the shear wall, was timber splitting around the concrete shear key a design issue? Did you need to reinforce the timber?
So around the shear keys at the bottom of the wall where we had the cutout, I guess we had quite a few cross layers in the CLT, and the loads weren't particularly, or we were comfortable with the loads there, and we used a conservative approach, kind of ignoring the cross layers, and also just considering it as a bit of bearing on the perp to grain, basically. So in that case, we found we didn't need screw reinforcing, but I can, if the loads were significant, kind of in the hundreds of kilonewton in shear or more, then you would certainly need some screw reinforcing, I think.
Yeah, a question saying, where do the services go?
Where do the services go? I'm not sure what building that is referring to. I think I talked about it in the Keith Drive building where there's a central core for the services, but for the Fast Epp building, the services were again majoritarily hid behind a bulkhead at the back of the building, where the stair cores and stuff are, and then would come out from there with ducts, and so it'd all be exposed. Generally.
A brief question saying there's no edge protection.
I'm not sure. I'm not sure if this is edge protection on the CLT floor plates. I'm assuming.
Referring to at the beginning of the presentation, there was a few buildings there. Oh,
right. Okay. It was possibly then in the Brock Commons building. I wonder if it's through the point supported CLT, where there's a floor panel landing onto a column with not much around it. I think there was there's a whole bunch of screws in the reinforcing in the top of it, and a whole bunch of testing was done, and a whole bunch of analysis was done to confirm that. That was a key driver for that system.
Yeah,
that's about as far as I know on that.
Yeah, a question saying, look like there is a lot gravity wall in major axis. How the lateral restrain in minor axis?
So I think this would be about the Fast Epp building again. The minor axis is restrained by floors where there is a floor. Where there's not, it's restrained by the landing of the stairs, which is again another piece of CLT, which drags the outer plane restraint to the end walls or the other perpendicular walls. So that was predominantly, so there was usually a weak axis support at each floor level.
Okay, the last two questions. With the pre-engineered beam column connection, how did the contractor get tolerance on the installation part of it? Was that an issue?
Yeah, it's certainly always a consideration, and some of those pre-engineered connections do have some tolerance issues, but typically when they are made, if you install them in the factory, so they come pre-installed on the timber, the timber is made to kind of millimeter or 0.0 tolerances, so it typically just clicks together like Lego. Where it doesn't work so well is if there's steel components in there that haven't been made to the same tolerance. So what I'd suggest is that the timber supplier would have some control over the steel components as well that are fixing to it. That helps to mitigate some of those issues, but it can be an issue. But it's just, I guess it's a function of the timber that they can make to such high tolerances that there is not usually as much of an issue.
Okay, we have to finish it in this question. Was the tectonus and the diagonal braces on every story or just at ground level?
My understanding was that they were all through the height of it, not just at ground level. And I think there would be different size. I think they were probably lumped into a bottom 3 or 4 stories, a middle section, and an upper one. Perhaps not required on the top. I'm not 100% familiar with the final details.
Okay, thank you very much, Andrew. That was really very impressive and interesting talk. We wish to see you once again in future for new buildings in New Zealand.
Yeah.
And thank you everybody who joined us today. And don't forget the TDS Roadshow, and thank you very much. Have a great day.
Cool. Thank you.
Bye.